A transformative shift is unfolding in research laboratories around the globe. Scientists are tapping into the extraordinary principles of quantum mechanics to develop computers that have the potential to revolutionize fields, from breaking supposedly unbreakable codes to simulating complex molecules for new drug development. Quantum computers promise to tackle problems that current technology can't address, but here's the twist. Most people are unaware of how advanced we've become or what's on the horizon. In this video, we're lifting the veil on the 8 stages of quantum computing, detailing our current position and what lies ahead. Prepare to explore a realm where particles exist in multiple states simultaneously and information can travel faster than light. By the end of this video, you'll grasp why tech giants are investing billions in this technology and how it might impact your life sooner than you expect. Let's dive into Stage 1, the quantum spark. In 1981, physicist Richard Feynman introduced a groundbreaking concept. He proposed using quantum systems to simulate other quantum systems, igniting what would become a technological revolution. So, why was this so significant? Traditional computers struggle with quantum problems. They're like attempting to create a 3D painting on a 2D canvas, always missing some elements. Quantum computers, however, operate fluently within the quantum realm. This is not merely theoretical. In 2019, Google's quantum computer completed a computation in 200 seconds that would take the world's most powerful supercomputer 10,000 years. This isn't just faster. It represents a different category of performance entirely. The quantum spark has been ignited, and it's unstoppable. But this is just the start. What follows will astonish you. Stage 2, Qubits, the foundations of quantum power. Welcome to the realm of qubits, where the principles of classical computing no longer apply. Unlike traditional bits that can be either 0 or 1, qubits can be both simultaneously. It's akin to having a coin that is both heads and tails at the same time. Here's where it gets even more fascinating. 2 qubits can represent 4 states at once, 3 qubits can represent 8, and so on, with the number of states doubling with each additional qubit. By the time you reach 300 qubits, you're dealing with more states than there are atoms in the observable universe. In 2021, IBM unveiled its 127-qubit processor, Eagle. Although this might seem modest, it represents a substantial advance. Each added qubit exponentially increases computing power. Scientists are racing to develop more stable qubits, exploring various approaches from superconducting circuits to trapped ions. Each method has its strengths and weaknesses, but all aim to harness the full potential of quantum mechanics. As we advance, remember that qubits are just the start. What follows will fundamentally alter our grasp of computation itself. Stage 3, Quantum Supremacy, the turning point. Quantum supremacy may sound like science fiction, but it's a real milestone. It's the moment when a quantum computer can solve a problem that no classical computer could solve in any practical timeframe. In 2019, Google claimed to have achieved quantum supremacy with its 53-qubit Sycamore processor. It solved a specific problem in 200 seconds, a task estimated to take the world's most powerful supercomputer 10,000 years. However, IBM challenged this claim, asserting that their classical supercomputer could solve the problem in 2.5 days. This debate underscores a crucial point. Quantum supremacy is not a fixed achievement but a continually shifting target as both quantum and classical technologies evolve. True quantum supremacy could usher in breakthroughs in cryptography, drug discovery, and financial modeling, but it also poses risks. A sufficiently powerful quantum computer could potentially undermine much of today's encryption, threatening global digital security. Stage 4, Quantum Error Correction, Mastering the Quantum Challenge. Imagine building a sandcastle while relentless waves erode your work. That's what it's like working with quantum computers. Qubits are incredibly delicate, and even minor disturbances can introduce errors. This is where quantum error correction comes into play. It's like constructing a seawall to protect our quantum sandcastle. By utilizing multiple physical qubits to represent a single logical qubit, we can detect and correct errors as they occur. In 2021, a team at Google demonstrated a logical qubit with a lower error rate than the physical qubits it was based on. This milestone proved that quantum error correction is not just theoretical but achievable. However, current methods require around 1,000 physical qubits for each logical qubit, which is why companies like IBM and Google are striving to build processors with thousands of qubits. Mastering quantum error correction will open doors to longer and more complex quantum computations. This isn't just a small improvement, it's the key to unlocking the full potential of quantum computing. And speaking of potential, hold on for what comes next. It's where quantum computing starts reshaping the world as we know it. Stage 5. Quantum advantage, from theory to reality. We've discussed quantum supremacy, but quantum advantage is where practical benefits emerge. This is when quantum computers can solve real-world problems faster, more cheaply, or more efficiently than classical computers. In 2020, a team of Chinese researchers claimed quantum advantage with a problem called boson sampling. They completed it in 200 seconds, a task that would take the world's fastest supercomputer 2.5 billion years. This isn't just about speed. It represents a whole new realm of possibilities. Quantum computers excel at certain problems that classical computers struggle with. For instance, in 2020, Google's quantum computer accurately simulated a chemical reaction for the first time, a breakthrough that could revolutionize drug discovery by drastically reducing development times. Financial institutions are also exploring quantum algorithms for portfolio optimization and fraud detection. Goldman Sachs predicts that quantum computing could become a $29 billion industry by 2021. As more fields discover quantum advantage, expect a surge in investment and innovation. But brace yourself. The next stage is where things get truly extraordinary. Stage 6. Quantum machine learning, the ultimate neural network. Picture a neural network that not only processes information but also manipulates the very fabric of reality to solve problems. That's the promise of quantum machine learning. Classical machine learning has already transformed our world, from facial recognition to language translation. Quantum machine learning, however, takes this to a whole new level. By leveraging quantum superposition and entanglement, quantum neural networks can explore vast solution spaces in ways that classical systems cannot. In 2021, researchers at the University of Science and Technology of China demonstrated a quantum machine learning algorithm that outperformed classical methods for a specific task. They used a 62-qubit quantum computer to solve a problem in 98 minutes, a task that would take the fastest supercomputers 8 years. But it gets even more intriguing. Quantum machine learning isn't just faster. It can tackle problems that are nearly impossible for classical systems. This could lead to breakthroughs in areas like climate modeling and material discovery. Tech giants are paying attention. Google has launched TensorFlow Quantum, a toolkit for building quantum machine learning models, while IBM is integrating quantum circuits into its machine learning workflows. We're on the cusp of a new era in artificial intelligence, and quantum machine learning isn't just an enhancement. It's a fundamentally new approach that could redefine what's possible in computation and intelligence. Stage 7. Quantum Internet, unhackable communication. Imagine a world where information can be transmitted instantaneously across any distance with absolute security. That's the promise of the quantum internet. The key to this is quantum entanglement, a phenomenon where entangled particles allow you to know the state of one by measuring the other, regardless of distance. Einstein referred to this as spooky action at a distance, and it underpins quantum communication. In 2017, Chinese scientists set a new record by demonstrating quantum entanglement over 1,200 kilometers using a satellite. This was more than just a lab experiment, it was a proof of concept for a global quantum network. Why does this matter? Quantum communication is inherently secure. Any attempt to intercept or measure the quantum information disrupts it, making it impossible to hack without detection. This could revolutionize areas like banking, government communications, and personal privacy. The race to build the quantum internet is already underway. The U.S. Department of Energy has unveiled a blueprint for a national quantum internet, the EU has launched a similar project, and China is operating a 2,000-kilometer quantum communication line between Beijing and Shanghai. As we approach this new era of communication, it's clear that the quantum internet isn't just an upgrade. It's a radical reimagining of how information is transmitted and secured. Yet, even this is not the final stage. What comes next will challenge our very understanding of reality itself. Stage 8, Quantum Simulation, Redesigning Reality. We've reached the final frontier of quantum computing, quantum simulation. It's not just about performing calculations faster. It's about creating virtual quantum realities that we can manipulate and study. Imagine simulating the precise behavior of every atom in a complex molecule or modeling quantum effects in a superconductor. These tasks are nearly impossible for classical computers but are well within the capabilities of quantum simulators. In 2019, Google's quantum computers simulated a simple chemical reaction. Although this might not sound groundbreaking, it's a significant step forward. As quantum simulators become more powerful, we'll be able to design new materials atom by atom, revolutionizing fields such as renewable energy and medicine. Some physicists even speculate that our universe might itself be a quantum simulation. If this is the case, quantum simulators could offer insights into the very nature of reality. Companies are already taking action. IBM has partnered with ExxonMobil to explore quantum computing for energy applications, and Volkswagen is using quantum simulation to optimize urban traffic flow. As we push the boundaries of quantum simulation, we're not merely solving problems. We're gaining the capability to reshape reality itself. The implications are both exciting and daunting. If you've made it this far, let us know your thoughts in the comments below. For more intriguing topics, make sure to watch the recommended video on the screen now. Thanks for watching.